Hi everyone, my name is Jason Gaitonde and I'll be telling you about our work on fractional pseudorandom generators from any Fourier level here at CCC 2021. This is joint work with Ishan Chattopadhyay at Cornell, Chin-Ho Lee at Columbia, Shahar Lovett at UCSD, and Abhishek Shetty at UC Berkeley. So what we do in this work is we give new constructions and analyses of fractional pseudorandom generators, which is a notion that was introduced by Chattopadhyay, Hatami, Hosseini, and Lovett in the Polarizing random walks framework to construct true pseudorandom generators. So what we do in this work is we're going to give a nearly complete interpolation between existing constructions of fractional pseudorandom generators that can leverage intermediate amounts of Fourier control. We'll also identify some weaker Fourier analytic quantities that now suffice for constructing PRGs in this framework. And then we'll also see some new applications of our results. So the plan for the talk will be, first we'll introduce pseudorandom generators, and then fractional pseudorandom generators in the Polarizing random walks framework. And once we've done that, I can tell you about our new results, namely which are new FPRGs from Fourier Bounds. Then we'll see some applications and connections, and then I'll sketch out the proof of one of our key results, which is really more about low-degree approximations of Boolean functions on subcubes. And then I'll end with some open questions. So the high-level goal here is we want to understand the necessity or power of randomness in efficient computation. And so in constructing pseudorandom generators, what we're doing is we're trying to construct a small or a simple distribution that nonetheless looks truly random to some important class of functions or to some computational model. If we can do so, then we can de-randomize such an algorithm. And pseudorandom generators are interesting for this reason, but they're also interesting because they have many applications and connections to other areas of theoretical computer science. So with that in mind, we'll define them as follows. We'll write script f for some class of Boolean functions. And then we'll say a random variable x is a PRG for this class with error epsilon. If it's the case that for any function in the class, the expected value of f on this random variable x differs from the expected value under truly uniform random bits by at most epsilon. And then we'll say x has seed length s if it's the case that you can write x as some function g evaluated on s uniform bits. So the PRG is stretching s truly uniform random bits to n pseudorandom bits. And so the goals here are that we want the seed length s to be as small as possible, and we'd also like the function g to be explicit. So the picture here is, here's the Boolean hypercube plus minus 1 to the n, and a PRG is just going to be some small subset of points that nonetheless this function class can't distinguish between it and the full hypercube. But here's another way to think about pseudorandom generators and what they're trying to do. It turns out that you can always extend a Boolean function f that's initially just defined on Boolean inputs via its unique multilinear expansion, also called the Fourier expansion. And in particular, you can write f evaluated on any input x as a sum over these f hat s, which are called the Fourier coefficients, times the monomial x to the s, where x to the s is defined as the product of xi for I in the subset s. And so this agrees with the original function on Boolean inputs, but this formula actually makes sense for any inputs for the values of x. And in particular, you can define or extend f in a canonical way to the solid hypercube via this unique multilinear expansion. And actually, these points turn out to have some meaning. So it turns out to be the case that if I evaluate this multilinear expansion at 0, the all zeros vector, then I'll exactly get the expected value of f under truly uniform random bits. And so rethinking about our definition from before, we can say that x is a pseudorandom generator for the class if the expected value of f is trying to approximate f of 0 now, up to some additive epsilon. And so with that in mind, we can now define fractional pseudorandom generators. And so the idea is we'll now allow pseudorandom generators to take fractional values inside that solid hypercube. They no longer need to be Boolean. And so the definition that was introduced by CHHL is that we say a random variable x in the solid hypercube is a fractional PRG for the class with error epsilon if it's the case that for any function in the class, we again have the same condition that the expected value of f on this random variable differs from f of 0 by at most some additive epsilon. And we have the same convention for what we want in the seed length. But now we actually have a new parameter of interest here, which is p noticeability. So we'll say a random variable x in the solid hypercube is p noticeable if it's the case that for any component of that random variable, the expected value of the square of that component is at least p. So another way to put it is that a pseudorandom generator is a one noticeable FPRG, because a pseudorandom generator needs to have Boolean values, so plus minus 1. But what that means is in our fractional pseudorandom generators, the larger p we can take in this definition, it sort of means the closer we are to a true bona fide PRG. And so again, the pictures to keep in mind are, here's the same PRG picture I showed you from before. We have this small subset of the Boolean hypercube. And again, the goals in constructing a PRG is you want the seed to be small and you want it to be generated from some explicit function. Now the picture for an FPRG is we're now allowing our points to be inside the solid hypercube. And again, we're going to want our seed to be small. We're going to want it to be explicit, but now we'll also like it to be p noticeable for as large as p as we can. So in this picture, if all these points have components plus minus root p, say, then it'll be p noticeable by our definition. So what's the use of these fractional pseudorandom generators? What do they get us? So CHHL showed actually a very general method by which you can convert independent p-noticeable FPRGs into a true PRG for any class that's closed under restriction. And when I say closed under restriction, what I mean is that for any function in the class, I can fix any subset of the variables and keep the function in the class on the remaining inputs. And so the idea that they show is that you can use your new independent fresh copies of your FPRG to take steps inside that Boolean hypercube. So the pictures, let's say you start at 0, then you add your first FPRG, then using their composition gadget, you can use your next independent copy of the FPRG to take another step, then another step, and so on. And what they show is actually such a process polarizes, and in particular, it'll on average get close to the boundary, at which point you can just actually round it off to a Boolean value. And so what they show is that this process indeed generates a true pseudorandom generator that's Boolean valued. And the total error of this construction is the number of steps you need to polarize to the boundary times the error per step for each copy of your FPRG. And what they show is actually this polarization happens relatively fast. In particular, it takes O of log n over epsilon divided by p steps to polarize. So what this means is what we want in our FPRGs in this polarizing random walks framework, what we want is that we have large steps, namely that it's p noticeable for large p, and that per step it has small error and small seed. So again, what we're going to do in this work is we're going to give new analyses and constructions of FPRGs, which we can then just put into the CHHL gadget construction in this polarizing random walks framework. But why are FPRGs actually just easier to construct? It turns out to be the case that we can oftentimes use very cheap pseudorandom primitives to construct FPRGs, and it can be done in an easier way than it would be for constructing PRGs directly. And so here are some of these primitives I'm talking about. For instance, k-wise independence, which means the expected value of this random variable on any monomial of degree at most k is 0. Delta bias spaces, which means essentially it fools all monomials or parity functions. And then this k-wise delta bias notion, which kind of combines the previous two. All of these are relatively cheap primitives that we'll see actually are very easy to use for constructing FPRGs. So to show a case where it's very easy to construct FPRGs, we need to define a few things. So a key parameter in the existing PRG literature is this notion of L1 Fourier mass. And so we'll define it this way. For a class F of Boolean functions, we'll define L1k of a function f to be the sum of the absolute values of the Fourier coefficients at the kth level, so over subsets of size k. And then we define L1k of the class in the natural way, namely as the maximum over functions of their L1k. And then we say a class of Boolean functions has B-bounded L1 Fourier tails if it's the case that you can bound L1k of the class by b to the k for all levels k. I should note this is only a non-trivial notion for b significantly smaller than n. And what CHHL showed is that it's actually very easy to construct fractional pseudorandom generators for such a class. So let's see how this is done. So one thing they show is, for instance, if my class is B-bounded L1 Fourier tails, then a scaled version of an epsilon bias space will fool it. It'll be an epsilon FPRG. And in particular, we'll start with a epsilon bias space Y, and we're going to scale it down by 1 over 2b. And you'll notice this is 1 over 4b squared noticeable because every component in this random variable is plus or minus 1 over 2b, and our definition considered the squares of it for noticeability. But why does it have error epsilon? Well, the proof is actually pretty straightforward. So recall that we want to bound the difference between the expected value of f on this random variable from f of 0. And so first, let's write it in the Fourier expansion. Then let's use the triangle inequality. And now let's use our definition of x as being equal to c times y to pull out these factors of c for each monomial here. And then by the definition of an epsilon bias space, all of these monomial terms are at most epsilon, so we can pull that out. And now let's rewrite this sum over subsets by sums over levels, so we collect the terms at each level. And so we get epsilon times this sum over c to the k times L1k. But by assumption, the class had B-bounded L1 Fourier tails. And note that because we chose c to equal 1 over 2b, we get this following geometric series. And so we can bound the total error by epsilon in a pretty straightforward way. One thing I want to note is we really crucially used the fact that we needed the Fourier bounds at all levels at this last step to make this geometric series. And so this is pretty interesting actually, because it turns out that many well-known classes of functions satisfy these L1 bounds. So for instance, read-once branching programs do, AC0 circuits do, and many others. But there's actually a couple other forms of these bounds that I want to show you. First are depth D parity decision trees. So Girish, Tal, and Wu here at CCC 2021 showed that they have L1k bounded by something that looks like k times root d times log n taken all to the k. Similarly, CHHL showed in their original work that F2 polynomials of degree at most d satisfy an L1k bound of the form k times 2 to the 3d taken all to the k. So what I want to point out about these last two bounds are that they somehow have this k inside the exponent. So they're taking something like k to the k here. And you might notice that in that previous argument that actually wouldn't have been good enough, because otherwise we can't get this sort of geometric series. So now that we've talked about this, I can tell you what's been known about this polarizing random walks framework. So we're going to assume the class F is closed under restriction. Recall that was needed for this polarizing random walks framework to succeed. And so the original work of CHHL showed that if your function class is B-bounded L1 Fourier tails, this framework will actually yield a PRG whose seed is something like b squared times poly log n over epsilon. And then later work by Chattopadhyay, Hatami, Lovett, and Tal showed that if the class satisfied just level 2 bounds, namely L12 is at most, say, b squared, to remain consistent with our definition of b-boundedness, then you can actually construct an FPRG such that this polarizing random walks framework will give a true PRG whose seed looks something like b to the 4th times poly log n divided by epsilon squared. So you'll notice actually, so there's a little bit worse Fourier dependence here, which is to be expected as they assumed a lot less. But they also have this error term that's now inverse polynomial. And that's exponentially worse than what was obtained in the CHHL construction with full Fourier tails. And so the moral is kind of from prior work, we understand what happens at the extremes. And what seems to happen is we get this large trade-off between Fourier control and seed length, and especially with respect to this error dependence. So some questions that were asked previously in these works were, how about the intermediate regime? So can Fourier bounds at intermediate levels help give better seed length or error dependence? And in particular, can you interpolate between those two seed lengths that I showed before? And a more philosophical question that was asked by Chattopadhyay, Khatami, Hosseini, Lovett, and Zuckerman last year in Stock was that, is L1K really the right Fourier quantity for constructing these FPRGs? And in particular, they actually speculated that a weaker Fourier quantity, which I'll call MK, might actually suffice. So what we're going to show in this work is that actually the answer to both of these questions is yes. So before I can get to our new results, I need to define this new Fourier quantity MK. So we define MK of a function f to be the maximum over Boolean inputs x of the absolute value of the sum of f hat of s times the monomial x to the s taken just at the kth level. And then we define MK of the class to be the maximum over functions. And notice that if actually your class is closed under negation as well as negating some of the input variables, then this formula actually reduces to just the maximum over functions in the class of this sum of unsigned Fourier coefficients at level k. So in particular, it's clearly always at least as good as L1k because there's no longer any absolute values inside. So with that, our results are as follows. For any Fourier level k between 3 and n, if I have a bound of the form mk is at most b to the k, and no other assumptions on the Fourier spectrum, then one can construct an FPRG such that this framework will give a seed whose length is as follows. It'll be k times this b squared times polylog n over epsilon term that was from the CHHL construction, times this term in red, which looks like b squared over epsilon, which looks a lot like that CHLT construction at level 2, but taken to a power that is inversely related to k. So in particular, this term will vanish with k. And so for k equals O of 1, this will actually yield significantly better seed length than CHLT, which assumed just level 2 Fourier coefficients. And it turns out that actually if we also have these L1 bounds for the lower levels below k, then you can remove this k factor over here and also improve some of the polylog terms. But the upshot is for, say, epsilon equal to 1 over poly n, we actually need bounds on just O of log n levels to exactly recover the CHHL analysis, even though they assume the full Fourier tails. And so as a quick application of this, let's return to this F2 polynomials example I mentioned earlier. So in the original work of CHHL, they conjectured that the class of F2 polynomials of degree at most d satisfied these B boundedness condition. In particular, they assumed, or they conjectured, that L1k is at most 2 to the O of d taken to the k. If this were true, then their result would immediately apply a PRG whose seed length is something like 2 to the O of d times polylog n over epsilon. And this would actually give an alternate construction of PRGs for this class that nearly matches the state of the art due to Viola. But as a corollary of our work, remember the bounds that we do have, which are that L1k is at most k times 2 to the 3d taken to the k. So the CHLT FPRG, which assumed just level 2 control, it gives you something, but it can't handle error even like epsilon equals 1 over root n. On the other hand, our new FPRG, which we have a bit more flexibility in, we can choose the level k we want. So if we choose k to be something like log of log n over epsilon, then we actually obtain a new PRG for this class whose seed length is 2 to the O of d times polylog n over epsilon. So in particular, for our construction, we can use these weaker Fourier bounds to basically match what CHHL would get with this conjecture. And so the takeaways I want you to have are that, for one, this polarizing random walks framework is perhaps a bit more flexible than previously known, but also this idea that we hope will have applications going forward, which is that you can actually use these weaker Fourier bounds by tuning them appropriately, now that you're allowed to choose the Fourier level. And one thing I want to note is also CHLT later conjectured that the same class of function satisfies L12 bounds of, say, order poly d. But a possibly easier question now is it true that mk of the class is at most, say, poly of k log n and d taken to the k? Even just k equals 3 would give an exponential improvement for this class. But why do I say it's possibly easier? Well, there's two reasons. One is that, as we saw, mk is at least as good as this L1k, so certainly it helps you in that respect. But the other is actually that this later work of Chattopadhyay, Hatami, Hosseini, Lovett, and Zuckerman, they showed actually how you can bound mk using correlation bounds, in particular with the XORs of shifted majority functions. And actually, this connection between mk and correlation bounds goes a little bit deeper. So subsequent work by Viola actually showed that new correlation bounds are necessary for mk bounds for F2 polynomials. So there's this interesting connection between mk in the existing literature on correlation bounds. So now let me tell you a little bit about how we obtain our improvements. So let's revisit the argument we had from before, but let's take a step back and not apply the triangle inequality too early. So again, this term on the left is what we were always trying to bound. And let's split it into two terms, which are the low degree part and the high degree part. And here we're defining f greater than or equal to k of x to be the sum of all the Fourier levels evaluated at x of levels at least k. So this is the low degree part, and the term on the right is the high degree part. So the low degree part we'll be able to fool using some form of k minus 1 wise independence, one of those primitives I mentioned before, depending on what assumptions you're making on the class and what's going on the Fourier levels of that class. What about the high degree part? Well, we know that it's going to be small if all the components of x are sufficiently small, just because all the terms are of degree at least k. But remember, the goal in constructing FPRGs is that we want steps as large as possible. So what we really need to do is we need to understand this f greater than or equal to k polynomial. And again, our goal is we don't want any dependence at all on the higher Fourier terms. So somehow we're going to need to beat the triangle inequality to improve on the argument from before and avoid needing any full Fourier tail bounds. And we're going to do this via new inequalities on low degree approximations of Boolean functions on subcubes. So one of the main things we show is the following. Again, suppose f is closed under restrictions. Then for any scalar c between 0 and 1, any level k less than n, and any function in the class, we can bound the maximum of this term, the high degree part of f evaluated at x, for any x in this subcube here, by a term that looks like c over 1 minus c taken all to the k times this mk term from before. And if we can do so using the argument a couple of slides ago, that means we can construct an epsilon over mk taken to the 2 over k power noticeable FPRG. And the reason for that is because we can then take c to be something like epsilon over mk taken all to the 1 over k and make this whole right-hand term be at most epsilon. And again, I want to reiterate that this is the place where we're getting this new and better Fourier dependence. And so now let me sketch this result out for you. And so first consider the toy case. First, suppose that f is exactly degree k. Then this is actually very easy to see because this is just homogeneous then. It's just every term is degree k. And so by homogeneity, we can actually just pull out a c to the k term and get something that's bounded by mk of f. So in general, obviously, things don't have to be degree k exactly. So we need to argue that these terms higher than degree k aren't hurting us too much. And the idea behind this is just for any smooth function, it's the case that it locally looks like its low degree Taylor expansion, which for us in this case, because of this multilinearity and the fact it's a polynomial, exactly just is its low degree Fourier expansion. So the idea will be as follows. Again, remember we're trying to bound this high order part of f at this point x. And so the idea is we're going to express this as a Lagrange error of a Taylor expansion of some other function. And you might recall that the Lagrange error form for any nice enough function is just some kth order derivative at an intermediate point. So here at some point Sx lying between x and 0. And so if we were taking kth order derivatives at the point 0 for some function in our class, we would just get level k Fourier coefficients. In general, we're not doing that here. We want to take them at some point Sx. But the key idea is that let's find a way to rewrite the kth order derivatives at Sx as kth order derivatives at 0 of some different function. And the key to do this is by doing a random recentering trick. Namely, by using random restrictions, it turns out you can actually recenter your function about Sx, so it's now taking the role of 0. And we can do this in a way that keeps it in the convex hull of our class using this closure under restrictions property. And if we can do this, then it turns out that things are bounded by MK, and then doing a little bit of calculus and algebra, you'll exactly recover the bound I stated before. So to just summarize, what we did is we gave a nearly complete interpolation between these existing FPRGs that allow us to leverage intermediate amounts of Fourier control. And then we also showed how this weaker Fourier quantity, MK, will now suffice for constructing PRGs. And then as a consequence of these, we saw some new applications and connections. So I just want to leave you with some open questions that are left open by our work. The first is, do M2 bounds suffice for constructing PRGs? So you might have noticed I mentioned that you can get something for MK where K is between 3 and N. And there's a slight gap here because we know how to get it from L12 bounds via that CHLT construction. So one natural question is, can you obtain a PRG using just M2 bounds? Another thing is I mentioned that you get this improvement if I have an MK bound and I also have these L1 bounds below it. One question is, does this still hold if I just have MK bounds? A big question, of course, is do such MK bounds hold for F2 polynomials? Because if so, then we get new PRGs for this class. And in general, a natural question is, are there other techniques beyond that considered by CHHLZ for bounding this MK quantity? An interesting question is more about understanding the relation between MK and L1K. So in particular, is there an explicit family of functions that has large MK, but also has a large gap between MK and L1K? And then the last question sort of goes beyond this work and the past sequence of works, which is that we've now seen a couple different ways of constructing FPRGs from Fourier bounds, and to some extent, we sort of understand the connection between Fourier bounds and what kind of PRGs you can get. But the original polarizing random walks framework of CHHL is a bit more general than this. So a natural question is, can you construct FPRGs going beyond this sort of Fourier analytic framework? And with that, thank you so much for your time.